Okay, so today we're very happy to have Baptiste Cercle, who will talk about three-point correlation functions in the SL3 Toda CFT.
Right, so thanks for the introduction of our invitation to speak in the seminar. So the goal of this presentation will be to present some recent progress made in the understanding of a certain two-dimensional conformal field theory called this SL3 Toda CFT. So to be more precise, I will try to present to explain how certain fundamental observables of the theory, so-called three-point correlation functions of vertex operators, can be rigorously computed using a probabilistic framework. So this talk will be based on a series of works together with Rémi Rode and Vincent Vargas, as well as Yishao. So before moving on, let me mention that if you have any question or if something is unclear, please do not hesitate to ask me. Interrupt. So to start with, what is this SL3 Toda CFT? So the SL3, from a very high level picture, the SL3 Toda CFT is first a quantum field theory. For us, we think of a quantum field theory as a model, a theory which is defined using a random function, a quantum field random function. In the case of this SL3 Toda theory, the random function that we study takes values in a two-dimensional surface. It will be the two-dimensional sphere S2, and has values in a real vector space. Note that here the random function will have values in a two-dimensional real vector space, and this is one of the main differences between what you may be used to have usually, like for instance, Liouville theory. And the fact that it has values in a two-dimensional vector space will have major consequences in its study. The model will be actually much more complicated to understand because of this fact. Okay, so this SL3 Toda CFT is the study of a random function. The question is, how do you prescribe the law of this random function? So to do so, there is a powerful method in the physics that you may be familiar with by now, which is called the path integral, and which is a way of defining, at least formally, a random measure, and therefore provides a way of picking at random such a function. So the way it proceeds is you start with an action functional. Here it is this S gamma, and this action functional takes a field and gives back a real number. And the thing is, the measure you want to construct will have under this measure, you will have a tendency to see fields which are close to the minimal of this action. So this is the way of sort of quantization of this least action principle. So a way to do so is, taking this expression with the integral. So you integrate over all functions from the sphere to R2, and you average using this action functional. And of course, the measure element that you consider in this definition is purely formal. It stands for some Lebesgue measure on the space of functions, so it does not really make sense. But in some examples, when the action functional S gamma is nice enough, you can define it using probability. So I mentioned the Liouville theory earlier, and the reason why is that this SL3 Toda CFT is actually a natural generalization of Liouville theory. The main difference between them being that the field has no values in a two-dimensional vector space rather than a one-dimensional vector space. In fact, the construction using the path integral is quite similar to that of Liouville theory. The action functional are almost the same. It's just adapting this setting to the Liouville action functional to this two-dimensional setting. But despite the similarities, the Toda theories are much less understood than the Liouville CFT. There have been a bunch of works in the physics by all these people, but these Toda CFTs, there are not a lot of questions that are still not clear, not answered today. even in the physics literature. Okay, so one nice aspect of this SL3 Toda CFT is that it is a conformal field theory. So there are many ways of defining what is a conformal field theory. Depending on which background you have, on what kind of definition you want to have. So for us, you can think of this model, as being somehow behaving nicely under reparametrization of the sphere, which is a way of rephrasing this Gavetsky axiom, which says that conformal field theory is a model covariant under conformal transformation. But there are actually many other ways of defining a conformal field theory. Should it be concerned with geometrical operations, such as gluing of surfaces, which resemble the Segal axiom, or more algebraic or geometric ones. But what's interesting with this SL3 Toda CFT is that in addition to this conformal symmetry, it has actually a higher level of symmetry, which is called the W or higher spin symmetry. And while conformal symmetry is encoded by this Virasoro algebra, this W symmetry is encoded by so-called W-algebras, which are rather complicated objects. So there are no longer Lie algebras, but there are rather vertex operator algebras that contain the Virasoro algebra as a subalgebra. Of course, there are many reasons for us to study this Toda Conformal Field Theory. Should it be from the point of view of W-algebras, which are rather being studied at the moment from representation theoretical viewpoints, or should it be thanks to its interplay with other models that are studied by physicists, such as WZW models or model of statistical physics at criticality, or because it is a general framework of the AGT correspondence. Okay, so far, imagine that we have been able to define this theory, this quantum field theory. The next question that you might be wondering, you might want to ask is, how can we understand this theory? So it is quite usual to say that the knowledge of the theory is accessible via the computation of certain observables, the average value of certain observables. In the case of this SL3 Toda CFT, these are the correlation function of vertex operators. So you would say that you have fully understood the theory as soon as you have been able to compute all the correlation functions of vertex operators. So what are these correlation functions of vertex operators? So they are just functional of the field, which are indexed. This is a family of functional which are indexed by a weight alpha, which belongs to this two-dimensional vector space R2, and also on the point Z on the sphere. They are quite simple in the case of the Toda CFTs, and just exponential of the field scalar product with alpha. And if you want to compute this correlation function of vertex operable, or vertex operators, what you do, okay, is just you take this expression of these vertex operators, you use the path integral definition, and you just compute the average of this observable, this product of observables, with respect to the measure defined above, using this exponential minus the action. But the issue is, of course, you cannot compute the correlation function in such a way. Since the path integral is nice, you have a nice expression, but you cannot. It's not retractable. You cannot compute them in practice. You cannot use this path integral to compute the correlation functions. So to remedy this issue, there is a powerful method in the physics now called conformal bootstrap, which, instead of studying this path integral, studies the symmetries of the model. To be more precise, what happens is that, okay, I know that my model has a certain level of symmetry. So what I do is that first I will study the algebra of symmetries of the model. And then I will come back to my actual model by saying that it's just a representation of this algebra of symmetry. There is a representation of the algebra of symmetry hidden somewhere in the model. So in the case of Toda, so what you are naturally led to do is study of Highest representation of W-algebras. And if you do so, then you have actually a lot of constraints imposed on the model. And all these constraints imposed by the symmetries after proper representation theoretical study, all these constraints show that the knowledge of a conformal field theory reduces actually to that of two fundamental items, which are first the structure constants of the theory, which are really specific to the theory, and these are just the basic correlation functions, that is with n small. In the case of Toda or Liouville, n will be equal to 3, so the structure constants are just 3-point correlation functions. And the second ingredient that you need to understand this conformal field theory is the conformal bootstrap procedure, which is a recursive procedure to compute all correlation functions based only on correlation functions, on the basic correlation functions. And to carry out this procedure, you need some universal objects which are called conformal blocks. So this means that if you want to compute all the correlation functions of a CFT, what you need to know is first to compute the structure constants, and then secondly, understand how to carry out the conformal bootstrap procedure. In general, you have these conformal blocks which are universal. They do not depend on the theory to carry out this conformal bootstrap procedure, but you still have to determine, the spectrum and the central charge of the theory. So the goal of today's presentation will be to provide a first step toward the derivation of this conformal bootstrap procedure in the setting of Toda theory by explaining how certain structure constants of the theory can be computed. And to this end, we'll show that a probabilistic definition of these 3-point correlation functions is given by an expression predicted in the physics literature by Fateev-Litvinov, which takes the following form, which is a bit nasty, I would say, which involves a bunch of special functions and everything. If we have time, maybe I will try to sketch what the bootstrap formalism would look like for the SL3 Toda CFT. At least I will try to explain how we can implement it in the simple case of 4-point correlation functions on the sphere. So the plan of the presentation is as follows. So first of all, I will explain something which you are a bit familiar with, I guess, by now, which is the path integral interpretation of the theory in terms of Gaussian field and Gaussian Multiplicative Chaos. And then I will explain how we can see the symmetry enjoyed by the model through the existence of wide identities, which translate in probabilistic terms as Gaussian integration by parts, actually. Then I will explain how reflection coefficients naturally are necessary to understand this theory and how they arise in this probabilistic setting. And eventually, we will see how all these ingredients put together allow us to derive this formula for 3-point correlation functions. And finally, the bootstrap formula, if we have time. So before moving on, do you have any question, comments? Okay, let's move on. So first step is the probabilistic construction of this SL3 Toda CFT. So our goal is to give a meaning to the formal path integral of our fields. That is, the physicists define the law of a random function by saying, okay, I take the average value with respect, there is a weight, but otherwise it's just a uniform measure of functions weighted by this exponential minus the action. In the case of Toda CFT, okay, this action is as the following form. You know that it closely resembles the action of Liouville CFT. The only difference is that instead of taking, you need to take scalar products because your field is two-dimensional. And the thing is, you have actually one additional exponential potential compared to Liouville. In Liouville theory, you have this exponential gamma phi. In Toda CFT, you have two such exponential potentials. And the thing is, you need to take, okay, you have your two-dimensional field, and these two potential just corresponds to your field projected in some direction of the space. And these two directions should be not collinear, but that is, it should be a basis of R2. But you still have, the coupling constant gamma, and you also have the background charge Q, which is now a vector. But otherwise, the action is really the same as in Liouville. The only change is that you take a two-dimensional field, and you need to adapt a little bit the definitions. And then, what is common is to split the action between two terms. So the first, the quadratic term, which is in blue, it just corresponds to the measure with respect to, it's just a Gaussian measure, so you can interpret it in terms of Gaussian free field. And here we will interpret it as the probability law of vectorial Gaussian free field, so a two-dimensional Gaussian free field. So the properties of this two-dimensional Gaussian free field is just, okay, imagine that it has two independent. If you take an orthonormal basis, then on each component it has independent. The components are two independent Gaussian free field. Of course, one thing is that you need to add this constant mode, this zero mode, this TC variable, to remedy the fact that Gaussian free field has zero mean, zero average over the sphere. Okay, so you are interpreted the first term in the action, and then you need to make sense of this exponential, the remainder terms in the action. And you have this exponential of the Gaussian free field. The Gaussian free field is not a well-defined function; it's a distribution. So you need to make sense of the exponential of the field. For this, you need the theory of Gaussian multiplicative chaos. That is to say, the field does not really, the exponential of the Gaussian free field does not make sense as a well-defined function, but rather at a random measure. So you can define the random measure exponential gamma dv, and if you do so, you end up with a well-defined probabilistic object. And the nice thing is that the object is compatible with what you expect from the physics. That is to say, it behaves covariantly under conformal change of variables. So if you're interested to the expression of the correlation functions, the correlation function take the following form. So you're first a prefactor, which is just a product of gamma function, which is irrelevant, which is completely explicit, sorry. And then you have an explicit dependence in the z variables. But in part in these correlation functions is that it can be expressed as expected value, at moments, joint moments of correlated GMC measures. That you take two GMC, so you have two potentials associated to two free field, two GFS associated to the vectors E1 and E2. You take the Gaussian free field associated to these two GFS, and you take two GMC measures. You take the average value of this GMC measure. You take some moments, and this gives you the correlation functions up to some explicit prefactor. And of course, there are assumptions under which this expression makes sense. And the bounds are the following, and they will be crucial in the sequel. So the first one, is the fact that the singularities which arise in this Fi must be integrable with respect to the GMC. The second one, just amount to saying that the moments of the GMC do not explode, do not blow up. So you cannot take arbitrarily large moments of GMC measures, all the more if there are singularities. And this second assumption simply corresponds to this fact. Okay. So we have been able to define, to make sense of this path integral. And now we have probabilistic theories that we want to understand. So the next step in the understanding of the theory is the understanding of the symmetries enjoyed by the model. And the symmetries can be seen via so-called word identities. The thing is, up to now, I have not specified that, I have not given any precision on this basis that we consider in the action, this basis E1, E2. In general, if you take any basis, the model that you will work with will be a conformal field theory, but the conformal invariance does not provide enough symmetry to you know, there's not enough constraint to understand the model. You need to have additional constraints on the model to understand it, and these additional constraints can be added by considering a special basis of R2. By special is meant that this basis should be associated to some root system of semi-simple and complex algebra. So here, this means that E1, E2 are given by precisely these vectors R2. So the thing is, you cannot, if you take any basis of R2, you don't have enough constraints. But if you take these very special vectors, then you will have extra constraints arising. And then your model will satisfy certain identities which encode this new level of symmetry. So we prove with Yishao that word identities were present in actually all on the model, and they take the following form. So the first one is with an insertion of the stress energy tensor. You know, stress energy tensor just simply encodes conformal symmetry of the model. And this first word identity is exactly the same as in Liouville. You see that what you have on the left-hand side, so it's just a correlation function in which you have inserted one stress energy tensor. And on the right is some differential operators applied to correlation functions. So you have L minus one. L minus one simply is the descendant of the vertex operator. So you can think of if you are used to this language of primary fields and descendant fields, you see that L minus one L is just the L minus one descendant of the field. If you're not used to it, you can just think that L minus one L is just derivative of the correlation functions with respect to the variable Z. The thing is, if you want to do the same for W, so there is another in the SL3 Toda CFT, there is also another holomorphic current, is W higher spin tensor. And if you want to reproduce the same scheme, then you have one identities, but the thing is, this one identities involves W descendants. So you see W minus one and W minus two. While L minus one L can be expressed as just the derivatives DZL, it's not the case for the W minus one, W minus two descendants. So this quantity are not differential operators, but they really corresponds to descendant of the primary fields. If you don't know what is a primary field, okay, imagine that you just define new objects starting from correlation function. You can actually define new objects. Okay, how do we prove such identities? Well, the proof is simple. It's just that the stress energy tensor. What is it? The stress energy tensor is just functional of the field, which is completely expressed in terms of the field. And so in the end, using probabilistic framework, you see that you just need to plug in this expression into expectation, and then you do Gaussian integration by parts. And of course, computations are really messy, but you can handle this. And the same procedure works also for W, but the computations are much more involved, a lot more involved. Anyway, okay, so having proved the word identities is the first step toward integrability of the theory. In that, we now have a confirmation that the model has the desired symmetries. But starting from these local word identities, we can also derive global word identities. And these global word identities, what they show is that there actually exist constraints between the descendant fields. The most simple of these constraints is the following. So sum of the L-1 descendant is equal to 0. And what does it mean? Okay, if you remember that L-1 L is simply derivative with respect to the ZL variable, then the latter is nothing but saying that correlation function are translation invariant. So this global word identity somehow carry the information about global conformal invariance of the correlation functions. There are a lot of constraints, and there are actually, 3 associated to this stress energy tensor, 3 associated to conformal invariance, and there are 5 such constraints between W descendants associated to this higher spin symmetry. So you see that you have 3 constraints stemming from conformal symmetry and 5 ones stemming from this higher spin symmetry. You can also add more constraints on the fields by considering vertex operators with special weights. For instance, if you assume that the weight of your vertex operator V alpha is in some special, very special direction of the space, then actually you can relate the W-1 descendant and L-1 descendant. So these are just proportional actually. And you can also have other constraints if you take even more special values for the field. That is, if you prescribe that it takes values of the form, is a weight of the form minus gamma W1 or minus 2 over gamma W1. So you can add constraints on this descendant field in doing so. And if you have a lot of constraints, a lot of equations, and if you combine all these equations, you end up showing that a certain family of 4-point correlation functions satisfy a differential equation. And thanks to this differential equation, you can show that a family of correlation functions of the form V alpha 0, like as written, can explicitly computed up to a multiplicative vector. So this C gamma, which is nothing but a structure constant. So this W symmetry allows to compute these 4-point correlation functions up to this structure constant. Question is next: how do you deduce the structure constant from this explicit expression? In physics, what is usually done is you perform operator product expansions. That is to say, you study like you perform Taylor expansion when 2 points collide. Here you see you have a function with depend on the variable z, which has an insertion at 0 on z. So what you do is you look at the behavior of the correlation functions when the z variable goes to 0. And in doing so, you have 2 vertex operators which collide, which get closer and closer and collide. And so it is assuming in the physics that when you study such asymptotics, then you have an expansion which is completely explicit and which takes the following form. You have 3 terms expansion, it takes the following form. Here the coefficients b gamma are completely explicit, the exponents are completely explicit. So this provides actually an alternative expansion for the 4-point correlation functions. And this new expansion is written in terms of, this coefficient b gamma and 3-point correlation functions. And these 3-point correlation functions, they stem from the fact that, when you collide these 2 points, then you have other vertex operators which are involved. Okay, so you have this alternative expansion. So if you combine the results that we explained before with this new expansion, the expansion derived thanks to the word identities, with this new expansion, then you show that these structure constants satisfy a set of shift equations. Oh, okay. So you have this shift equation, and starting from this point, as soon as you have these shift equations, then you can deduce the formula that I presented at the beginning. Since this formula uniquely characterizes this shift equation, uniquely characterize the Fateev-Litvinov formula up to multiplicative factor. Okay, so in principle, this should finish up, but there are a lot of issues actually. So one issue is that the structure constants that are involved in this expansion do not necessarily make sense probabilistically because of the cyber bonds. Indeed, sometimes that what I explained before. Remember that the correlation for the correlation functions to be well defined, they need to satisfy scalar product of alpha minus q scalar ei is negative. The geometric interpretation of this is that alpha, the weight alpha, lives in this probabilistic region in that. And the thing is, the 3-point correlation functions that were involved before in the shift equation, the weights must go out of this probabilistic region. And therefore, we need to make sense probabilistically of the correlation functions when the weight alpha do no longer belong to this probabilistic region, but goes in the other region of the space. Okay, so for this, it is assumed in the physics that actually, if you want to go from one such cone, such wedge to the other, you can use the fact that you work with early algebra and use the fact that there is the well group which actually sends this wedge to any other wedge. So you have 6 elements in the group, and you know that these 6 elements sends one chamber into the other. Can send one chamber to any other chamber. So the only difference between two vertex operators defined with weight rated via such a transformation is that you will have a reflection coefficients. So in Liouville, you know that you may remember that you have this relation in the physics. V alpha equals to R alpha V 2Q minus alpha. So this is the exact same thing in the setting of Liouville of Toda CFT. So if you want to define the correlation functions outside of the probabilistic region, then what you simply have to do is that you use an element of the well group to send your weight inside the probabilistic region, define the probabilistic region there, and then use multiply the correlation function by the reflection coefficient. Of course, it's purely formal, but nonetheless, it is possible to prove that if you do so, then actually it's not that formal. You can actually prove that this definition is a good one, since the probabilistic structure constants can analytically continued by doing so. And you know that the issue, okay, if your weight alpha only stays in the probabilistic equation, the 3-point correlation functions are analytic, it's not so hard. The issue is what happens when you cross one border of the chamber. But anyway, this can be done, you can study it, and you show that if you do this, if you use this heuristic from the physics and extend the 3-point correlation functions with this relation, then you have an analytic function, which is rather nice. And how do you prove such a statement? You actually rely on the fact that these reflection coefficients, which are, you know, coefficients which really come from the study of the conformal field theory, they actually arise in tail expansion of correlated GMC measures, which is quite remarkable, I think. Okay, so last point is another issue that I did not mention before, which is that the 4-point correlation functions studied in the one identities may not actually make sense from a probabilistic viewpoint. So we've seen that the first constraint, how to remove the first constraint of the cyber bonds and the alpha. But there is another constraint in the cyber bonds which say that moments of the GMC measure may not blow up. And if you want this to satisfy this second assumption, that the moment of the GMC measure do not blow up, then you cannot define your 4-point correlation functions. So this is completely different from the Liouville theory. In Liouville theory, these 4-point correlation functions are well defined. In Toda CFT, this is not the case, and you need to extend the range of validity of the probabilistic representation. And for this, you need to go beyond the cyber bonds. And the first step in the derivation, in the extension of these cyber bonds, is the study of the tail expansion of correlated GMC measures. So this statement shows, okay, statement, you may not see at the moment why it's relevant to extend this cyber bonds. But, okay, this statement just says that if you take this correlated GMC measures and you want to study the asymptotic expansions, then actually you can explicitly compute the expansion using reflection coefficients. And you know, this statement is quite remarkable because you have a purely probabilistic object on the one hand, which is correlated, which are correlated Gaussian multiplicative measures, and you can relate this purely probabilistic object to quantities that are really coming from the physics, these reflection coefficients. And if, okay, now that we have this asymptotic, you can extend the probabilistic definition of the correlation functions by simply removing these extra terms in the asymptotic of the GMC measures. And so if you define the correlation functions in such a way, you know, by taking this exponential of the GMCs, and you remove the terms which contribute to the asymptotic, then the map that you define is analytic, and so that it's the good continuation of the correlation functions beyond the cyber bonds. It's a bit what was done in the proof of this FZZ formula, you know, by adding this -1 term to the exponential to the inside the expectation. It's exactly the same thing. You remove the -1, but you need to go a bit further than -1 in the expansion. And the corollary of this statement is, you know, an extension of the range of validity for which the DOZZ formula holds, and which is the following. So the difference, you know, in the paper by Vargas, this DOZZ formula was proved to hold and was expressed in terms of moments of GMC measure. And the constraints were just that, this sum alpha 1 plus alpha 2 plus alpha 3 minus 2q was greater than this, this bound. Thanks to this, to the knowledge of this tail expansion of a Gaussian multiplicative chaos measure, we are actually able to extend the round of validity of this probabilistic representation. Okay, that was functioning, I think. Okay, next, it's more probabilistic slide. So I'll try to explain to convince you that reflection coefficient naturally rise in the tail expansion of correlated GMC measures. So why is it the case? So you know that the tail expansion of correlated GMC measures, when you do so, you can, you use the radial angular decomposition of the GFF so that everything reduces to, so you know that if you take the circular average of a Gaussian free field on circles of radius a exponential minus t, you have a Gaussian free field, a Brownian motion. So in the end, it should not be too surprising that if you want to study the expansion of correlated GMC measures, then you actually end up studying planar Brownian motion. And you have a drift because your GMC measures have singularities. So what you do, okay, if you want to understand the maximum, the expansion of GMC measures, so you want to understand, okay, the maximum of this process, this drifted Brownian motion. So what you do, okay, you condition the value of this maximum, and then you want to understand the law of the process conditioning the value of this maximum. From the one-dimensional case, this is just Williams path decomposition. So here I have simple, okay, it's just a Brownian motion with negative drift. And Williams path decomposition say, okay, this Brownian motion can actually be sampled by first, sampling the maximum of this process M with respect to its marginal law, and then sampling two independent processes. First, processes which is a Brownian motion with opposite drift until it reaches M, and then a Brownian motion conditioned to stay below M. You can actually do the same in higher dimension, and you end up proving a Brownian path decomposition, which takes the following form. So here is drawn a planar Brownian motion. If I want to sample such a Brownian motion, what I can do is, okay, first I sample the maximum in the direction of the simple roots. So the process will have, since it goes, in this region, in the direction, which will have a maximum with respect to the simple roots E1, E2. So you can sample this M1 and M2 with respect to the marginal law, and then run a first diffusion process until it reaches the boundary of this wedge. Then you can launch a second diffusion process, which will hit the other boundary of the wedge, and then you can run a third process which will stay inside the wedge forever. And if you do so, then you end up with a Brownian motion with drifts. Of course, these diffusion processes are not as simple as in dimension 1. They are diffusion processes with rather complicated generators, but they enjoy really nice properties. I don't have time to explain, but yeah, it's really nice. And the proof of this fact relies just on the reflection principle. So if you combine all of the above, eventually you end up proving the desired formula. And you show that the probabilistically defined three-point correlation functions, so which can be expressed in terms of this Gaussian multiplicative chaos measure, are actually given by this crazy formula by Fateev-Litvinov. And you may know that here in this statement, you know that the probabilistic definition of this Toda CFT is for parameter gamma in 0 square root of 2. But here one subtle issue that you can prove this formula only for gamma greater than 1. And the reason for that is making sense of 4-point correlation functions in this range of parameters of gamma is already a mess. And if you want to go beyond, then you need to describe more precise asymptotic of correlated GMC measures, which may be possible, but is very technical, and actually it's not very interesting, I guess. Okay, so the next step in the conformal bootstrap procedure would be to describe this bootstrap formula, which expresses these 4-point correlation functions in terms of 3-point correlation functions on these conformal blocks. Okay, so let me say a word on this formula. So on the first line, you have a 4-point correlation functions. This object is defined using probability. You know the correlation function has been defined using these GMC measures. However, inside these correlation functions, you notice that you have alpha 1 and alpha 4, which has generic points, generic weights. You can take any alpha 1, alpha 4 in this probabilistic region. But this alpha 2 star and alpha 3 star, they need to be these semi-degenerate fields. They need to be, collinear to this omega 1 or omega 2. But nonetheless, if you assume that you want to compute such 4-point correlation functions with 2 semi-degenerate fields, then my conjecture is that you can write a bootstrap formula which closely resembles that of Liouville. And so this formula, what's inside? So you have this structure constants, which are given by the Fateev-Litvinov formula proved that I have just shown you before. And the second ingredient will be this conformal blocks FP of Z, which should be given by the AGT correspondence. And you know that since we have alpha 2 and alpha 3, which are semi-degenerate, these 3-point structure constants are indeed well computed. If you don't take, on the one simple thing is that if you don't take alpha 2 and alpha 3 to be these semi-degenerate fields, then it is not clear at all that such a formula would hold. It's actually really, really far from clear. Okay, so this is at this stage just a conjecture. The 24 is in red because maybe it's not 24, but something else, some 12, 48, I don't know. So this is still a conjecture, and there are many difficulties, many obstacles that we encounter before proving this formula. Actually, from the point of view of scattering theory, the diagonalization of the Hamiltonian is really complicated. It's a bit of a mess, but it's really interesting since it involves scattering symmetric spaces. Spend time on it. And after this bootstrap formula, there are still, of course, many other problems to be studied in Liouville in this Toda CFT. One of them is to investigate what happens with the theory of the boundary. Can we get some Fyodorov-Bouchot formulas for 2 correlated GMC measures on a circle? Why not? Another question is to derive the Segal axiom for this SL3 Toda CFT. This is not clear at all from the physics, but this should be doable. At least the probabilistic framework should suggest that it is possible. And another question, which is, I would not say $1 million question, but not so far, is to compute all structure constants of the theory. That is, 3-point correlation functions where you do not assume anymore that one of the field is semi-degenerate. There are no conjecture expression in the physics. Yeah, it's a very, very hard question. It's not clear that it will be possible to compute it today. Anyway, so thank you for your attention. If you have any question, please do not hesitate to ask.